All right, hello everyone. This is Amir Humansad from UMass Amherst, and this is a joint work with my student Milad and our collaborator Reza Shokri. And unfortunately, none of them could be here to present the paper for different reasons, including visa issues. So I'm getting the pleasure of presenting the paper. All right, so like was mentioned in the last talk, machine learning systems have found their way into many internet services, and a lot of the apps and systems that we use are leveraging and using some kind of machine learning models at the heart of their operation. And a convenient and common way of building machine learning into your system is using platforms provided by Google and Amazon, which is known as machine learning as a service. So suppose that you want to build an app, you have some data. These platforms provide you a training API that you use to train your model. So you use that training API, you train a model for any particular classification task that you're looking for. Okay, so like the attacker is just using the prediction API. It's probably one of your users of your app. And then if your data set, if your training data set contains sensitive information, then it's possible that that sensitive information is somehow leaking to the adversary. And this was also mentioned in the past talk, and there's different kinds of leakage through prediction API and from the training data set. And a particular type of leakage that we're interested in this talk is membership inference attack. So in this approach, the attacker's objective is to verify whether a particular data record has been used during the training process, right? So the goal of the adversary is to know whether a particular sample has been a member or not a member of the training data set. And this could be bad for different reasons. So suppose that you've trained your data set on data records from people with a particular disease, let's say some kind of cancer. And if I learn that your data record has been part of the training data set, then it leaks to me that, and it exposes to me that you have that kind of disease, right? And there's other kinds of more advanced attacks that can leverage and kind of use this simple membership inference attack as a stepping stone to do those attacks. So for instance, it could be used to learn features of some records. So if you want to learn if the particular record, the gender is male or female, you can feed different records with different genders into the training set. And if you're able to verify the membership of that sample, then that helps you to kind of learn the features of that data set. All right, so this is the membership inference attack. But then let's ask ourselves that what's the main reason that enables an attacker to leak that kind of information? The main intuition is that machine learning models tend to overfit to their training data set. And therefore, if you use a prediction API to input samples from the training data set and from out of the training data set, it's likely that the distribution of the output of the prediction API is different for members and non-members, right? So even if you're providing like pictures of a dog, the distribution of the output for the dog that was used during the training process would be different than the distribution of the output for the dog picture that wasn't part of the training data set, right? And this is only because it's not because of the type of the dog, but it's because you've trained your kind of machine learning model in that particular dog picture, and therefore it has overfitted to that particular type of dog. All right. And therefore, this could be used to build a membership inference attack. Previous work by Shokri and others had in fact shown that you can use machine learning to attack machine learning systems. So you can use, so if the distribution of the outputs for members versus non-members is different, then perhaps you can build a classifier that kind of trains on the distribution for members and non-members, and then based on that, you can use the trained model to attack the system and find the membership of different samples. All right, so this work has been done. And note that this attack is done in a black box manner. So the attacker is merely using the prediction API for both learning his classifier and also for kind of querying the model. And he doesn't know anything about the distribution of the data, the parameters of the model, and such, right? So this is a black box attack. All right, so one could think of some naive countermeasures to fix this kind of membership inference attack. So the first countermeasure is probably to limit the number of outputs that you kind of return during the prediction. So if you are kind of, if the job of classification is classifying objects and the output is like kind of scores for possible 100 classes, then you kind of restrict your prediction API to only return the top 3 or top 5 outputs, right? And this has shown, in fact, it's been shown by previous work that it kind of improves privacy. It kind of protects, it provides some level of protection to membership inference attack. But the problem is that it first of all severely impacts the utility of the application. And also, this approach doesn't provide any provable guarantees on privacy, right? It works, but we don't really know how much, what are the kind of guarantees on privacy. A second possible naive countermeasure is using differential privacy, right? So how about you obfuscate the output of your prediction API and add noise through differential privacy to your predictions? This approach does provide provable guarantees. The problem is differential privacy algorithms are not designed or don't care about utility, and therefore, if you use a regular differential privacy algorithm, this is likely to hurt the utility of your machine learning algorithm significantly. All right. Okay, so now let's talk about the approach we're taking in this paper. So we are trying to solve the membership inference problem, and the approach we're taking is that instead of manipulating and adding noise at the prediction API, we train the model in a way that it provides provable guarantee on membership inference attack. All right, so we, as opposed to adding noise at the prediction, we train the model in a way that ensures and guarantees protection against membership inference attacks. And we do this in a way that it also provides the best utility of the application, right? So solving this, we solve an optimization problem that not only defeats the membership inference attack, but also provides us with the best utility for the underlying machine learning application. All right, so let's see how we're doing this. So suppose that F is the machine learning classifier that we're trying to protect. So this is the model that we want to make sure it's not leaking membership information. So typically, if we don't care about privacy, this is how we train the model, right? So we have the classifier, we input our training data, possibly labeled with different labels. We train it, we feed these into the classifier. We have a loss function, we have to minimize it. We solve this optimization problem, and we train the model by kind of solving the optimization problem, which is minimizing this loss function. All right, so this is regular training without caring about privacy. Now, let's bring into the picture the inference attacker. So in this case, we also have an attacker. So in this case, model H represents the inference attacker. And this attacker has access to a subset of data records from your training data set. So like, suppose you have a big training data set, and somehow the attacker knows some of the members of your training data set. And he also knows some of the non-members of your training data set. And therefore, he has access. He has black box access to the classifier F. So what he's doing is that he feeds his samples to the classifier, obtains the output from the prediction API, and he does this for members, for the known members and non-members, and then based on that, he's building a classifier to distinguish members and non-members, right? Now, if you want to defeat membership inference attack, we have to minimize the accuracy of this inference attacker, right? So the objective, if you want to protect privacy, we have to solve an optimization problem that minimizes the inference accuracy of the model H. And then to have a good machine learning classifier, we also need to maximize the accuracy of our classifier F. And therefore, what we're doing here is that we're looking at this joint optimization problem. We train the classifier F in a way that it not only maximizes the prediction accuracy of F, but also minimizes the accuracy of the inference attacker. All right? Okay, so to solve this optimization problem, there's this classic approach in game theory, which is called a min-max game. So we trained a model by, so we train our classifier F by using the maximum gain of the inference attacker as a regularizer for the machine learning model F. Okay, so, and therefore to train the model, this is what we're minimizing. We minimize the loss function plus lambda times the maximum gain of the inference attacker. All right, so this provides privacy because during the training, we're already considering the strongest possible adversary, right? So like we're using the maximum gain of the inference attacker as the regularizer, and therefore any adversary will be weaker than this because we're already during the training are considering the strongest possible inference adversary. And it also provides the best utility for a given inference attacker because we're finding the best machine learning model by minimizing the overall loss function of the classifier, right? So we maximize utility for a given target, for a target privacy level. All right, so let's look at some results. We performed experiments using PyTorch. We used 3 data sets that are probably well known, at least one of them, Cyphar, which is a data set of images. Purchase is the database of purchase histories. And Texas is a database of hospital discharge from patients at a Texas hospital. And then for each of them, we evaluate the model and our defense on different deep learning algorithms. So because we want to implement this min-max game, we design an algorithm in an iterative manner. So the first epoch of the algorithm, we solve the optimization problem for the inference attacker. So we find the gain of the attacker. And then the second phase, now we optimize the loss function of the classifier, and we do this iteratively until we feel like we're getting close to an equilibrium point, right? So you see that in those figures, you see that we start from some point, and then we keep kind of optimizing the gain of the attacker and the loss function of the inference of the classifier. And at some point, we see that we're starting to kind of reach an equilibrium point, and that's the point that we use. We say we're done with training the model. Okay. All right, so let's look at some results. So the first point here is that we see that our model is able to provide membership privacy with very high degrees. So like for instance, in this case, for the purchase data set, we see that using our min-max training compared to the regular training, we are reducing the accuracy of the membership inference attack from 67% to 51%. And the best accuracy is 50%, which is random guess, right? So we're getting close to the random guess. So we see that there's a huge improvement in membership leakage. And on the other hand, this is provided with only, 3.5% of reduction in the utility of your machine learning classifier, right? So the price you're paying for having membership privacy is some reduction in the accuracy of your classifier, which is your utility, but it's not that much, right? It's only 3.5% here, right? So with 3.5% of utility reduction, we're getting a big jump in membership privacy. And we also see that, like I mentioned before, the intuition for having this kind of membership leakage and other kinds of leakage in membership in machine learning models is the fact that models overfit to their training data set. And here we're seeing that our approach is reducing the gap between the accuracy of training and testing data set, right? So we see that it's acting, our mechanism is acting as a regularizer and is closing the gap between training and testing accuracy. And this is why we're improving the privacy, the membership privacy, right? Because there's less leakage through the training process, right? So therefore, our mechanism can also be thought as a mechanism for regularizing the machine learning models, right? It's now with our algorithm, the trained machine learning model is better generalizable to samples out of the training data set. All right, so if the only thing it's doing is regularizing the model to protect privacy, so why not just using some standard regularization to fix the privacy problem, right? So the answer is yes. In fact, you can use standard regularizers like L2 regularizer to address the membership privacy problem, right? So you see that with specific values of regularization, you can achieve an attack accuracy very close to what we achieve with our adversarial regularization. But the problem is that other regularizers are likely to impact the utility of your machine learning model, right? By contrast, in our model, we're optimizing the utility and membership privacy as a joint optimization problem. And therefore, for any target privacy, membership privacy level, our algorithm provides the best utility for the application, right? So like any other regularizer that you use to reduce the impact of membership privacy, membership leakage will have a higher impact on the utility of your application. All right, and lastly, recall that we're training the model by solving this optimization problem, which is minimizing the loss function plus lambda times the maximum gain of the adversary. And the lambda parameter can be used here as a factor to trade off utility and privacy, right? So you see that with you can increase the value of lambda, and by increasing it, you'll have better protection on membership privacy. By increasing lambda, the accuracy of the attacker will reduce. But at the same time, it will also reduce the utility of your classifier, right? But the good news is that for values like 51% of attack accuracy, we're still getting a test accuracy which is very close to the case of no defense, right? So like we see that for 51% attack accuracy, the testing accuracy has dropped from 80% to only 76%, right? So we don't. So with we can get good privacy protection with very small degradation in the utility of your machine learning classifier. All right, so to conclude this paper, we have designed a mechanism to prevent leakage of membership from the training sets. And we've done this by solving an optimization problem that tries to find the best utility of the machine learning algorithm for the strongest attacker for a target privacy level. And we've shown that we can achieve good privacy with little degradation in the utility of your application. The code and data set is available, and thanks for your attention.
I think you are considering only a specific attack F. Can you do anything? Can you do anything for general attack?
What do you mean by general attack?
I think F is a very specific attack.
You mean other kinds of leakage?
No, for the membership. The F which you have there is attack, which is a very specific type, not general. So there might be some attack which can break your scheme very easy. So can you say
by specific, you mean a specific type of supervised learning algorithm? Is that?
I don't know. Some.
I mean, you can you can use the same min-max scheme for different algorithm. I guess the challenging part is to solve the optimization problem and find.
Yeah. Well, if you have another function, another attack F, you can maybe train that. But what can you say if you train this machine for only one F? Then what can you say for other type of attack?
Oh, I see. No, so one thing about this approach is that we're solving the problem for a given data set, right? Even if you train the model for a different data set, the solution will be different, right? So and therefore for different cases you have to solve it differently, right? So like even when you kind of if you train the model and now the training data set somehow changes, you have to update the parameters of the model with the new learned model based on the new min-max scheme.
So if someone comes up with different F, you have to train again. Okay.
Yep. With different, you mean data set, right? With different data set or different algorithm? Different attack, you mean other than membership inference?
No, the attack against the membership, but with different algorithm.
Oh, I see. No, it's so the thing is, we're in our model, we're maximizing the gain of the inference attacker, right? And therefore, we're considering the strongest adversary, and therefore other attackers. I mean, we're already in the defense are considering the strongest attacker.
Yeah, actually, for that point, I think you have proper guarantee based on the assumption you know the specific attacker's training data and the classifier selected by the attacker, like your F.
Right.
Like for example, in your model, you assume F is a 3-layer neural network, but actually an attacker could use a 4-layer neural network. So basically, the question is you don't know what classifier is used by the attacker and what's the training data the attacker has.
Right. So F is a classifier. You mean
F, the inference model of the attacker.
Okay. So F is the classifier.
So
you mean H, right?
Right. Right. H. So basically, you are a defender. You don't know what classifier the attacker will use. You basically make an assumption.
Yeah, I think that's true. So I think that's true. So like, so I think if you want to have the best, I guess you have to work with the best that you have. So if you feel like this is perhaps a strong enough model available to the adversary, then maybe we train it with this. If the attacker comes up with a stronger H inference model, then maybe that's probably some kind of mismatch between how much protection you can provide.
Right. Probably not even stronger. Like you assume a classifier attacker model, attacker use another model, maybe the guarantee is, I mean, no theoretical guarantee probably. Yeah.
Okay, so have you considered actually applying your attack and defense to commercial API, prediction API, for example, Amazon, Microsoft, and Google's, and etc. So looks like your evaluation is a little bit toy.
Yeah, the evaluation is on some models that we train.
So question is it really practical?
Right. I mean, the approach wouldn't be different, right? So I mean, the approach is, I mean, so probably, I guess the privacy advantage could be different if you use Google or Amazon, right? But I mean, the approach wouldn't change, right? It's the same thing. You use a prediction API. In our case, it was a locally trained model. In that case, is a prediction API you use. It's a good thing to also kind of try out those APIs and test this kind of mechanism on those, but we haven't done that.
So it would work against the black box model?
Yes, this is a black box defense, exactly.
Hi. In a lot of the examples that you shown, the success rate on the training data was 100% and say 80% on the test data. Okay, so the accuracy, yeah. So might it be that these types of that your type of defense, or this actually shows some type of overfitting of the model? So might it be that this somehow depends on the overfitting? If there was less overfitting, then your defense would have been less successful.
Yeah, that's a fair point. I think it depends how you're overfitting the model. So like, I guess if you look at these,
the more you overfit, the more probability that you have.
Definitely, definitely.
Thank you so much for the talk. I'm wondering, can you say a little bit more about countermeasure? Like suppose the paper is published and the attacker knows that defender is playing this min-max game, and how hard how hard is it for the attacker to actually still perform the membership inference attack, assuming he knows all the optimization, or is it not possible?
I mean, so in this case, I guess the attacker will know the extent of the kind of privacy he can expect from his attack, right? I mean, he can't do any better because, I mean, he can't find a countermeasure to this approach because in the min-max optimization, we're already considering the strongest attacker, right? So he can't use the knowledge of the existence of defense to come up with a better classifier for his inference attack. But at least he would know that there's a defense here, and therefore, if he builds a classifier, he would know that it only has maybe 51% accuracy of detecting members versus, I don't know, 6 to 7%. So I think that's the only thing that will give away to the attackers.
Thanks.
So during training, the Adversarial Regularization network had access to a portion of the target model's training dataset. When you, at test time, evaluated the accuracy of the attack network, did that attack network also have access to part of the original training dataset?
Yeah.
Okay. Mm-hmm. The same amount as the Adversarial Regularization network, or a different amount?
Yes, the same amount. Yeah.
Okay.
But the accuracy is calculated on the remaining part of the training dataset. Right. So the part he already knows, but the accuracy is calculated on the rest of the dataset.
Yeah, thank you for a good talk. In the utility function, you're trying to basically minimize the utility and at the same time the utility function, and at the same time you're trying to minimize the gain and the utility.
Minimize the maximum gain.
Yes, but don't you think there's a cases that this could be in conflicts, or the attacker can use this against you? So if you try to minimize the gain, maybe you will not do a good job in the loss part in the utility function. I'm just asking, is there potential of conflicts between protecting and increasing the accuracy of your algorithm?
Well, yeah. So this is. So if I get your question correctly, so you're asking how we can kind of manage the trade-off between the accuracy of the underlying model and the robustness to the attacker.
To the attacker, yes.
So like I showed in this kind of table, so we use the lambda parameter to trade off between how much privacy we're looking for and how much accuracy we want. So by tuning this lambda, we can say, I want to have more privacy. I don't care if the utility is going down by this much. Or you can say, I really care about utility, but let's fix the membership privacy only a little bit, right? So that's the parameter that you can use to tune between privacy level and...
Yeah, but can this attacker use this to make your overall accuracy, and the learning accuracy will be decreasing here in order to increase the robustness against the attacker?
Not quite sure what you mean by that.
Okay, let's talk about it online.
Right.
Okay, let's thank the speaker again.